Hi, everybody. So today I'm giving a presentation on simulating astrophysical plasmas in laboratory experiments. So this is going to be a bit of a talk about my work, about work that's going on in my lab, and some other laboratory experiments that are relevant to large-scale astrophysical systems. It's going to begin with a bit of a pedagogical, how do we do things sort of section, and then just a breakdown of my experiment. Oh, it's giving the speaker notes.
You can just try leave the show and then start again. For use slideshow.
I think that's going to be the best thing to do. How's that?
Yeah, that works.
Excellent. I don't have any speaker notes anyway. So, first, some introductions. Hi, I'm Dr. Quinn Morgan. I'm a third-year graduate student working with Dr. Paul Bellin. These slides will be provided afterwards. You can check out all the links in them. I was an electrical engineer at one other point in my life, and I like to read, I like to write, I like to play guitar, and I also work with wood. There, now you know a little bit about me. Hopefully I'm less intimidating. Everybody knows I'm a very intimidating character. In figure one, we see a student who's pretending to know what he's doing. So here's the outline. We're going to first go over MHD and scalability. We'll talk about how MHD applies to both small and large scale systems. Then we'll talk a little bit about experiment. What is it? Who knows? Ideally me, but we'll find out. We'll go a little bit over the pedagogy and then a little bit over the design. And after that, I'll give you a breakdown of the astrophysical plasma experiments that we have on campus here at Caltech. And then finally, we'll go over some other relevant experiments at other universities. This is just a smattering from what I know, given my limited experience. So diving right in. Magnetohydrodynamics and scale. Magnetohydrodynamics is a set of equations that a lot of plasmas are governed by. It's not the only way that we can describe plasmas. It's actually the simplest method that we have. We assume the plasma is a fluid, i.e. the particle distribution is Maxwellian. The temperature and pressure are typically not tensorial, though they can be, which means that you can have different temperatures and pressures perpendicular versus parallel to the magnetic field. We're not really going to talk about that. We also assume that the gas is sufficiently ionized and magnetized to exhibit emergent phenomenon. You don't need magnetization, it's just that that's typical. And these ionization fractions can be very low, actually. Some plasmas with less than 1% ionization are still perfectly well described by magnetohydrodynamics. So magnetohydrodynamics has 6 principal equations. The first is the momentum equation. It looks a lot like Navier-Stokes. That's because it basically is. It is a Navier-Stokes equation, assuming that your fluid also reacts to electromagnetic forces. So that's the momentum equation up there. We also have a continuity equation, which probably has a similar form to what you would expect if you've done any fluid work. It's basically just saying that the density inside a control volume stays constant over time. That which enters and exits sort of matches the change in the volume over time. We also have the induction equation. So if you're a fluids person, this is the first thing you probably won't recognize. This is basically describing how changes in the electrical topology affect changes in the magnetic topology. That's sort of hidden here because the dV/dt, that's describing the electric field topology. But you also expect that since this is a fluid, your ionized species can reorganize and there should be no net electric field. So it actually ends up describing the change in the magnetic field with respect to the curl of your fluid momentum and magnetic field cross products. On the right-hand side, we see there's also a current term involved, but that eta there is resistivity. So if that's 0, if your plasma is indeed an ideal conductor, it's just 0 on the right-hand side. Finally, we have the remainder of Maxwell's equations, but we kind of discard the divergence of E because we assume quasi-neutrality, i.e. in every control volume, there's an equal number of positive and negative charges. So that's the 6 sort of minimal equations for describing the plasma. We're not going to go into it in any significant detail. It's sort of just to say, oh no, this is complicated. But the really interesting thing is that these 6 equations are scale independent. On the left hand here, we have an astrophysical Oh, yes.
So you have a current.
Yes.
Separation of charge.
Yes.
Flow of charge.
Yes.
So why do you have divergence of E going to?
So The divergence of E goes to zero because in any volume you have the same number of charges. The density of charges is the same, but they can have different direction, like net momenta. And if they have different net momenta, that implies a current, even if the amount of charges in a control volume is staying the same. So that's why div E goes to zero, generally. You can actually have situations where div E goes to not zero, but we're not going to focus on that so much. MHD is scale independent. On the left-hand side, we see an astrophysical plasma jet. This is an intergalactic nucleus. On the right-hand side, we have a laboratory plasma jet. This is actually something that I produce in my lab frequently. We can describe both of these things with a set of dimensionless numbers, specifically beta, the Lundquist number, and gamma. These are basically describing the ratio of magnetic pressure to magnetic energy density to pressure energy density, propagation time versus resistivity, and isothermality versus adiabativity. These are all basically, well, they're two things. They allow us to scale systems from one critical length and speed to another, and they also characterize the balance of energy in the system. Does anyone have any questions about these? I see some people scanning them.
Well, is there some interpretation of the Lundquist number, like in one property?
Yeah. Yeah, the Lundquist number is basically the most difficult. It's the one that makes the least sense upon first glance. You can sort of see the beta is basically P over P. It's the pressure of the magnetic field versus the fluid pressure. This one is basically telling you it's relating the travel time of a shock through the system to the resistivity of the system. So it's telling you how quickly does like a magnetic or fluid, electromagnetic fluid shock propagate through the system, and how rapidly does that system accept changes in current. So if you have a very small Lundquist number, that indicates that resistivity is going to dissipate shocks before they propagate in a fluid-like manner. And if you have a very large Lundquist number, you'll find that the resistivity is generally propagating before it's, sorry, the shock is propagating before it's dissipated by resistivity.
So in this case, the speed of the shock is propagating speed.
Yeah, the most shocks in these systems propagate at the Alfvén velocity. In galactic systems, L is typically very large and the Alfvén speed is moderate. The resistivity is also moderate, so you end up with a very large S, which means that ideal MHD, assuming resistivity is basically negligible, is applicable. In the laboratory plasma jets, L is much more modest. The Alfvén number is higher and the resistivity is very low. So both of these systems have a large S, but it's not exactly the same. We'll get into that a little bit more. But the critical thing is that systems that have identical beta, S, and gamma will have the same physics. And you can scale between one and the other using scaling laws pretty easily. So if you take beta, gamma, and S, you can non-dimensionalize everything, normalize everything to some reference length and speed and time, and this is what you get. It's the same set of 6 equations, but you can disregard one, and they look a little bit cleaner.
You didn't mention anything about the position.
What's that?
You didn't mention anything about the position.
That's a good point. That's actually an excellent point. Back when we assume MHD, we are assuming collisionality.
Right.
So generally, this is going to apply to plasmas that are relatively cold. What's your name? Navi. Thank you, Navi. Maxwellianity is sort of produced by collisionality. So having a highly collisional plasma means your plasma is rapidly going to become Maxwellian, means MHD applies.
Right. So in your next slide, that you would also have
in this slide, or
yeah. So here you also not have any, but yeah, you're only dealing with collision. So,
yeah, it's a very restricted case. So anyway, that's sort of the overview of MHD and scaling. Now we'll get right into experiment. What is it? Let's find out. So pedagogy, what does an experiment look like? What do you want to get from experiments? How do you run experiments? Let's take a look at some tips and tricks, some ideas related to these questions. So generally, experiments are small compared to the original system. This is because you want to be able to interact and manipulate your experiment. So this on the right-hand side is a laboratory solar prominence. And on the left-hand side, that's an actual solar prominence. They're separated in length scale by a factor of 1 billion, which is very large. So this one on the right-hand side is about 20 centimeters across. If you wanted to, you could hold it in your hand. It would rapidly go away. It's 20. Oh, my bad. I did that one. Yes, it is 20 centimeters, not 2 centimeters. My apologies. The inner core of the solar prominence on the left-hand side is about 10 megameters. This is the largest solar flare ever on record, captured back in 2001. These things actually have slightly different topology, which we'll get into later, but the core, like critical elements are outlined there.
Is one of those X15 or X15?
I'm sorry, what did you say?
One of those X15.
Yeah.
X15
Yeah.
wiped out the electrical grid.
In fact, yeah, this one actually would have wiped out the electrical grid, but thankfully it was 90 degrees away from us, so we got lucky with that one. It was not as large as the one that destroyed the Canadian power grid in, I think, the 80s or something. It's just that one was never recorded. So anyway, these are very large systems. How do we actually model these real world forces in the lab? You might look at that and say, wow, sun is a really crazy thing. What do we do about that? Here are a couple sort of tips and tricks from an experimentalist to a set of theoreticians trying to design an experiment. You may have a set of goals. You want to simulate gravity, you want to simulate your electric field, you want to simulate your magnetic field, or maybe achieve specific current configuration. On the right-hand side, there's sort of a set of tricks that experimentalists have to do these things. To simulate gravity, you can use acoustic pressure. Plasmas being fluids will respond to resonators. So if you encapsulate a plasma in a resonator, you pulse it, and that will cause pressure waves to simulate gravity. So you might think, oh, it's really difficult to simulate a sun, but you can actually just have a microwave cage, a spherical glass bulb, and plasma inside it that you just strike with an RF field, and then you can actually get a radially confined plasma ball. You can also use RF electric fields to cancel out gravity. You'll see that later on when we go over some other experiments. So if you want to examine a plasma free floating in space, you can pulse an RF field to counteract gravity, averaging over time.
What's your typical plasma composition? Is it pure plasma or is it electron proton plasma or pure proton plasma?
It varies pretty widely, but for astrophysical plasmas, generally people are looking at the simplest plasmas to create. So that's going to be hydrogen plasmas, just proton electron with a little bit of neutral background gap.
But the goal would be to go with pure plasma in cases, right? What do you get?
Yes, actually, yes. There is a goal to examine pair plasmas. They're just very hard to create. When you say pair plasma, do you mean an electron positron plus? Yes. Pair plasmas are very difficult to create just because it's hard to find a source of positron. But yeah, there is a way to do it. I can actually link you to a developing experiment that is working with a pair plasma. It's more of a fusion based experiment, but they do have a plan to look at arched flux ropes made of pair plasma. But generally, will be you look at actual species, so you will have hydrogen, argon, or other easy to strike gases when you're simulating astrophysical.
So it's going to be electron proton.
Yes, electron proton.
I mean, you can't tell those two apart.
Right? No.
So I guess you're not actually simulating we wouldn't be able to simulate pair plasma with realistic dimensional numbers. Non-MHD, right?
Yeah, that's true. I mean, there are some things that will change. The only thing that I think off the top of my head is sensitive to that would be the Lundquist number, because the Alfvén velocity depends on both the ion and electron masses. But I'm saying that without checking a textbook, and experimentalists need to check textbooks frequently.
No, you're right. Yeah, the alpha number depends on the math, which depends on the plasma composition.
Yeah. So you can eke it out, but there are some higher order effects that you will only capture with partition function descriptions. Anyway, the rest of these are pretty simple. You have charged electrons and background field coils to apply specific magnetic and electric field configurations. And specific current configurations can be achieved with strategic magnetic reconnection and wire array. Yes, what's up, YouTube?
The later gravity pressure and electrical doesn't actually, but not precisely. Or in like trying to overcome that, something like I don't know, accelerated tempered so it feels more realistic implementation.
So far as I know, there is not. You basically people try and configure these things such that you can ignore gravity. That's sort of the ideal way to run these things. You could, spin the chamber. You could do any number of things. The drift equations, if you're familiar with them, if you can find a way to apply a net force to a plasma that is insensitive to the charge, then you can cause the plasma to drift one way or the other, and that will be actually no, sorry, that is sensitive. You can use electric fields to simulate gravity, but you can't really escape the excitation that you're describing. You'll induce splitting. You'll do all sorts of things, but generally you'll know your electric field. So, anyway, so there's a set of tips and tricks for taking something theoretical and making it experimental. So when we do this, what do we want? We want to seek insights into observed phenomena and predict unexpected or unseen emergent phenomena. There may be things that we haven't looked for out there in the real world that we see in our experiments really easily. Finally, how do you run an experiment? Typically, these things are really high dimensional. You have a lot of knobs to turn, which means you're going to need a lot of grad students. I was just working through this recently, and I think it's a very instructive little example. How many people here are familiar with Buckingham pi theorem? Okay. Yeah. I'll describe it briefly, but basically, a guy named Buckingham was like, hey, if I have a system that has a bunch of dimensions, each of those dimensions is a basis vector. So if you treat those as a basis vector, you can rotate your experiment into a space where you have some minimal set. And it makes it a lot easier to probe the space. But the trade-off is that you're no longer just twisting your current knob to 10 amps. You're twisting your current knob to 10 amps and your voltage knob to 500 volts or whatever it is. You have to do those things in concert. But you end up with less points to probe the space. So say you have some heat energy that is a function of the area of a thing, the length of a thing, and the current density for it. That implies that there's some relation F that relates A, L, I, and Q in such a way that the whole thing comes out to 0. These parameters have these different dimensions. You'll see that only one of them is dimensionally independent from the others, meaning it's a dimensionally independent, it's a unit vector. So you have to break the other ones down into unit vectors, and a very simple examination of the null space of your dimensional matrix says P equals n minus k, 4 minus 2. You have two dimensionless parameters. Did I think that right? Yes, I did, because Q is also dimensional. So you can actually rewrite this relation in a space that relies on pi1 and pi2 instead of A, L, I, and Q. Now, if you want to scan this whole space with 8 points per dimension, you go from requiring 512 measurements to just 64, which is great. So as experimentalists, these are tricks that we have to make our work a little bit more manageable. But it doesn't always work out in our favor. Plasma, just from the momentum equation, has 5 independent variables and 1 dependent variable, which implies a relationship between 6 variables all going to 0. This is our dimensional matrix. To probe this space with 8 points per dimension requires over 32,000 measurements. And if we go through the same process, we find, oh no, so does our reduced parameter space. So no matter what, probing experimental parameter space takes a lot of time and effort. You're going to need a lot of graduate students. So the simple answer to how do you run an experiment is with lots of people and lots of time. So now that we have an understanding of what these things are for, how do we design one? How do you make a versatile experiment? How do you measure it? How do you run an experiment? So these are highly interdisciplinary systems. Building a plasma experiment requires knowledge of bulk power to get power into your system, vacuum systems to simulate the space environment, and an actual understanding of plasma physics. So there's a lot of different convergent things, meaning really you just need to have a broad team. My lab is nominally 8 students, but we also have our professor who bears the brunt of the actual physics knowledge, 2 engineers who work on the vacuum systems and electrical components, and together the 11 or 12 of us makes the whole thing work. So for a versatile experiment, you need a highly interdisciplinary team. A lot of these experiments are collaborations, as you'll see.
Details the hyperlink.
Yes, they are. Would you like to see the details? Okay, so you activated my trap card. So I actually modified my candidacy presentation for this presentation, and I was really scared during candidacy, so I won't put you through this, but this is a diagram of our ignition system. In order to do pulse power experiments, to simulate all of this current flowing into a plasma, you need to be able to turn on switches really fast. So we have these things called ignitrons, which we trigger. The ignition trigger basically closes this thing, and these capacitors, the primary discharge capacitors, dump a huge amount of current into our plasma. The rest of the system is basically safety. A huge overhead goes to safety because an actual human person has to operate this stuff. So yeah, that's a little bit of the details. If you want to go over that later, we can. But I'm taking a lot longer in the intro than I expected, so I'll zoom through the rest of it. So we do need to measure things. This means you're going to have to design your experiment with a lot of access. So on this small experiment chamber, we have 6 viewports, 8-inch viewports that allow us to capture a large solid angle of optical information, any kind of EM emission. We have a multitude, I think something on the order of 32 vacuum ports for inserting physical probes, like Langmuir probes, et cetera, et cetera. This is a breakdown of some of the probes that we have. I'm not going to go over this, but if you want to check it out on the slide later, these are really useful things, which you may not have heard of from experimentalists. A lot of these are pretty simple because I have not had to design a lot myself, but they do things. They are used for detecting plasma frequency, density, magnetic field intensity, backing out current, doing energy spectrum analysis, emissions analysis, lots of simple things. What's up?
Why camera?
Oh, because
like the other ones.
the cameras, well, actually here, I think if I zip forward, damn, I should have put the lifetime on this. Plasmas in the lab, because you're scaling everything down, your length scale goes down by a factor of a billion. A lot of these astrophysical plasmas are around for millions and millions of years. But if you scale everything down, they're now around for millions and millions of nanoseconds. So the total lifetime of these things is frequently under a millisecond, meaning to get a camera that can image at that rate, you have to expend a lot of money. So sometimes people use diodes instead because you can get a continuous signal, and then you're limited less by a CCD and more by a digitizer, which is a lot easier to make faster. So finally, how do you run an experiment? This is sort of a joke slide. The answer is carefully. Every lab is different. You will have standard operating procedures that are sort of specific to it. So you just have to be careful whenever you enter a lab. Finally, let's get to the actual interesting stuff. Here's a set of laboratory astrophysics experiments at Caltech. Some of these I work on personally. A lot of these are run by my colleagues. I'll tell you about them to the best of my ability. So we have 3 primary astrophysical experiments at Caltech. We have the Caltech Jet experiment. This simulates astrophysical jets with stars and nebula. So think AGNs, YSOs. It's more applicable to YSOs than to AGNs. That's just how the scaling laws work out. It does not simulate relativistic jets, of course, because we can't accelerate a plasma that fast in the lab easily. We also have a single and double loop experiment. This is for simulating solar coronal loops and emerging flux ropes in situ. There are other experiments that are dedicated to that, but we'll talk a little bit more about the topological differences later. And finally, the ice dust plasma experiment. This simulates low ionization fraction plasmas with embedded water ice. These are found all over the place in space and even in terrestrial systems. It's a little bit of like a totally different thing than the previous two, but it has a lot of astrophysical relevance. So getting right into the first one, this is the caltech jet experiment. It produces an MHD-driven plasma jet. We can tweak the bias magnetic field strength of the gas volume. This is what the chamber looks like, so it's pretty big. It's actually 400 gallons. And it's on the smaller side of experiments involving jets. We have a electromagnetic, we can configure our electromagnetic topology with these electrodes and these bias coils. So we get a simple dipole magnetic field, that's our background field, and a background electric field from the anode and cathode, which are charged to respectively -5 kilovolts and 0 volts. So this is a pretty high energy system. It expends at peak about 60 megawatts worth of power. That's instantaneous though. The typical plasma parameters you get out of it are roughly 2 electron volts with a density of 10 to the 21 to 10 to the 22 per cubic meter. The relationship between these numbers and astrophysical numbers are actually not captured extremely well by scaling laws, but not a huge deal. So this is what it looks like on the inside. These are our electrodes. The outside of the chamber is pictured up there, right there on the left. So you can already see that there's some interesting things we have to work around here, right? Like we have 8 split points on the inner and outer electrodes, meaning that our initial topology is actually fundamentally constrained by the mechanics of our system. So when we do scaling laws, we assume the boundary conditions are the same for both systems. We actually can't make that assumption perfectly at the beginning of our experiment. Here's a GIF of the jet that we produce. Forgive the quality. Another thing you find with these cameras that are operating at these speeds is that they, don't have extremely high resolution. You can also see that this whole thing is about 12 microseconds long. Each exposure is 20 nanoseconds.
What is the size of the?
Oh yeah, that's a great question. So this is pixel number on the axes here. The jet at max is roughly 0.6 meters. So it gets pretty long. But what you're seeing in here, this is less than half a meter.
So why is how is this like astrophysical?
Well, I will show you. So this basically models the kind of jet that you see from a protoplanetary nebula or an active galactic nucleus. And in the next slide, I'll give you a little bit more of a look into the topology. This is basically just the best picture I could find on short notice. There are better ones out there. What's up?
So just like before, do you need any debouncing around the center, or you're just like sufficiently strong?
The magnetic field is sufficiently strong that we can just ignore it. Oh yeah.
The Earth is around the
Yeah. Let me show you. I prepared the detailed slides for the professors, but you guys are the only ones that have asked. So the K instability is triggered when you don't satisfy the safety condition. That gives you a radial acceleration outwards, which causes the RTI. So you kind of correctly identified that typically when you talk about the fluid RTI, you have a light fluid underneath a heavy fluid. So rho greater than rho naught on the left hand there, and a gravitational force downwards. Here, because the rope of plasma is accelerating outwards, we have a effective gravitational acceleration downward. And this is not a perfect vacuum. In fact, it's experiment, nothing is perfect. So this is roughly, I think, 10,000 times less dense than atmosphere, and this is 100 times less dense than atmosphere. So we basically have a super light fluid on top of, a super dense fluid on top of a super light fluid, even though both of them, yeah. So that's how that works. Are there any other questions?
Can you go back to the animation? Yeah. So this Is this like this is a burst of,
Yes, this is a burst.
so the real system is like sort of that or?
Yes, it is, but the scaling laws are also scaling time. So this has some lifetime associated with it. Here it's roughly 20 microseconds.
Yeah.
When you scale that up, it gives you millions and millions.
So that's like the time that your probes are.
Yes. And that's actually one of the reasons why this is better suited to YSOs than AGNs, because AGNs are much longer lived because they have a much higher magnetic field.
So this is sort of like what the dimension.
Yeah, exactly. So this is a cartoon of the actual model that we're working off of here. If you have a protoplanetary disk and a young accreting star, there's some dynamo-like action. You probably knows a lot about that. It charges up that accretion disk. The magnetic field, sorry, the star gives you a background magnetic field, which is generally dipole-like. So you have this background magnetic field, this radial electric field, and a charge separation. Eventually, instabilities cause currents to flow, and that gives you this jet that comes out of the pole and induces a toroidal field, giving you an overall helical topology. This is pretty much what we have in the lab here. So we have our electric field, which I think I may have actually gotten the polarity wrong, but we can switch it if we'll. We have a radial electric field. Our bias coil gives us a background dipole field. And as we close the whole thing and let current flow through the gap, we end up getting this current arc that gives us the same sort of field topology. So I hope that answers your question. And of course, it should be known that this is a model. It's not actually concrete. How stars get, how accretion disks get charged up and these jets begin to flow, but this is a solid representation of that model. And it scales well to observe phenomena in actual space. This is sort of what you see. There are two ways to do scaling. You can use this this set of scaling laws right here. C1, C2, and C3 are related to VA, beta, and F, or you can just compare VA, beta, and S straight across. So for our lab jet with hydrogen and a YSO jet, these are sort of representative numbers. We actually have pretty good agreement on everything except for S. That's the least critical one to have complete agreement on, though, because large S, that's much greater than 1, is basically just saying this is an ideal. So if you're willing to take that rather large difference in terms of magnitudes, both of these things are ideal. And they have the same alpha in speed and the same beta, typically. Are there any questions? Yeah, so that's the jet.
So with the Lundquist number, there is a strong lower limit of 4,
Yeah.
which is required to trigger reconnection.
Yeah.
In your lab plasmas, if your Lundquist number is smaller than that number, it's an absolute quantity, then you might not trigger the physics that's happening in reconnection.
That's a great point. That is a great point. We do actually. Sorry, I cobbled this together from a number of publications from my lab because I haven't had the time to reproduce all of these things in 2 years. But since the publication of this particular thesis that I took these numbers from, we actually have observed most likely Hall MHD reconnection. I don't remember how that modifies, if it modifies the Lundquist number requirement, but we are seeing higher Lundquist numbers in some scenarios.
Higher than larger than 4.
Yeah, I couldn't speak much more to that, though, unfortunately.
Yeah.
But yes, no, that is a good point. That not all of our plasmas will reconnect.
Yeah, and it's not just reconnection; it's also the rate at which it reconnects, which determines how much energy goes to the plasma.
Okay. You know, I given that I'm sort of a young graduate student still, and I'm coming into this field with not a lot of experience beforehand. Still learning a lot. So I'd love to talk to you about that later if you don't mind.
To your lab.
Yeah, absolutely. You can get the slides and you can get my email from it. There's still plenty of time, so I won't speed up too much, but I'll go a little faster. We also have a solar loop experiment. This is very similar. The triggering mechanisms, a lot of the underlying structure is the same. The one thing that's different is the electromagnetic topology. We have two bias coils instead of one, and we have different electrode configurations. This chamber is much smaller. Primary point of contact with this is my colleague Yang Zhang. You can get his email there and ask him questions about this system, and he is more than capable of answering. He's very smart. We get similar plasma parameters in the solar loop to the jet experiment.
Does this email not have a G?
It does not. Yeah, it confused me. So this is what our system looks like here. At the upper left, we have a solid model of the electrode structure. We've got two solenoids behind two half semicircle electrodes with an injection point in the in the center. We pulse gas in the same way with a set of fast gas valves, and we induce breakdown by charging up the electrode, and we get a plasma arch from one electrode to the other. Our vacuum field that the plasma is interacting with is sketched on the lower left. It didn't come out great in the presentation, I'm sorry. You can see it's rather complicated because these things are they have countercurrent in them. This on the right-hand side is a GIF of what we see at the result. We have this loop which evolved outwards to radius increases, we get a density dip in the center, and really Taylor instability and a little bit of reconnection sometimes at the outer edges when the plasma filament snaps. Any questions about that?
Yeah, this thing that you simulate or that you produce in your lab doesn't look like solar coronal.
Yeah.
The coronal loops form. Eventually, they reconnect. Then the loop just gets out. Do you see that?
Yeah, no, actually, you've already hit on a great point. This is a slightly different story than the jet. The jet does a really good job of modeling at least one well-accepted model of how jets form. The loop does not.
Yeah.
You can see a lot of similar phenomena, but that might be more just like fundamental plasma behavior than anything else. This is a comparison of one solar coronal loop to our laboratory plasma that I've taken from one of Young's publications. You can see the kink instability, you can see reduced strand radius, and eventually the strand breakage in both. You can see the same kind of wavy filamentary structures in both the laboratory and astrophysical system. And the time between each one is roughly, it scales. It may not obey scaling laws, but it scales, meaning that these things are happening at the same time, but not necessarily because they're exhibiting the same physics. That's because we're not modeling what is the most accepted system. Here, most heliophysicists take the three-component arcade structure as the sort of accepted model for how solar coronal loops work. That includes this rather obvious X point in the magnetic field topology, a current path, and a return current sheath. So you end up with this rather complicated structure, which we don't actually have. We don't have an easy way to simulate that X point, especially given our field topology. So we're representing a more simple arcade model, which has been used in the past and does apply to probably a limited subset of systems. This is an actual image, an average 3D model of our field structure taken by using a bunch of dot probes and averaging over many, many shots. There's no obvious X point. It's much more just a kind of twisted loop. So this is not the same system, actually. We still see a lot of interesting dynamics. It replicates dynamics of the real system, but fundamentally, it does not observe the same topology. So it serves sort of a different purpose. And it's interesting because we've learned a lot from this thing, it's sort of like a failed success story, if that makes any sense. Yang can speak to a lot more of the details. This is, again, just what I know. But we did do some scaling anyway. This is from former student Magnus Haas thesis. And if you sort of cast aside okay, we need the same boundary conditions, the same starting and ending topology, and just go ahead and compare one straight across. Then when you scale everything up, there's actually really good agreement across the board, except for with G. The force of gravity is just orders of magnitude off. What this implies is not necessarily that the laboratory plasma is evolving with the same physics, but rather that the physics governing it are this. Sorry, I don't know how to put this. It's the same set of processes that you're inducing. They're just not happening the same way at the same times. Anyway, what this is really great for is examining the behavior of arc flux ropes, because regardless of its correlation to the actual magnetic topology of the astrophysical system, it's still giving you a look into flux ropes interacting in space. So we took this thing and extended it to look at cross flux tubes, anything that can merge. On the right-hand side, this is sort of the updated version of that experiment. We now have two loops that can interact. On the left-hand side is an image from there. What we generally expect is that these things will reconnect and sort of form two different loops with, I think, counter helicity to preserve the overall helicity of the system, but I can't quite remember off the top of my head. This one has sort of been offline for a while, so I actually can't speak to it much, but it is interesting, so I wanted to put it up. Finally, crossing out of the jets and loops section and into the ice dusty plasma. This is headed up by my colleague, Andre Nicolau. You can reach him at the email there. He basically built this thing from scratch and he knows it inside and out. This is designed to simulate a wide variety of states and terrestrial plasmas, including noctilucent clouds, Saturn's rings, molecular clouds, anything where you have a not strongly magnetized plasma with a dust in it. Noctilucent clouds and Saturn's rings are actually particularly applicable because they have water ice in them. And that's what we use to form our dust grains here.
Does magnetism matter in these kinds of systems?
Not so much, no. It can. It's just that in these space plasmas, you don't see large-scale coherent magnetic structures. Saturn's rings have a background field because Saturn has a magnetic field. It's just not very strong, if I remember correctly. So magnetic fields will play a part in these systems. It's just that they frequently don't because they're small or not doing anything interesting.
And many of these are quasi-neutral plasmas. Right? So what's your neutral species?
With that?
What's your neutral species?
In these experiments, generally we have a background gap of hydrogen or argon. The gas is ionized to a low ionization fraction by RF coupled electrodes. So the whole thing is radio frequency coupled. You have a very fast pulsing electric field. This does two things. It makes it easier to ionize the gas, and it also counteracts gravity. So this is technically a gravity-free system when you average over time. This means we have primarily a neutral background gap, typically argon, and electrons floating around, and typically argon 1 and argon 2. What Andre will do is he'll inject water, which then spontaneously nucleates to form ice grains, and those ice grains charge up because electrons hit them. This is a very collisional isothermal plasma, so your ions and your electrons are the same temperature, meaning that ions are always slower than electrons. So the flux of electrons to ice grains is larger, and the ice grains have a tendency to charge negative. This produces some really interesting behavior because you get these large-scale icy structures in the plasma, And you can treat this as sort of like a slab from one of these space and terrestrial plasma. Microscope cameras allow for imaging of individual grains, and FTIR spectroscopy can be used to examine phase. So you can vary temperature and pressure with your cold heads and background gas to examine how that changes the phase of the ice and if that affects their development over time. What's that?
What are the players? In fluorescence?
Something infrared. I'm sorry, I should know that, but I actually don't. All I know is it's a broadband infrared spectrometer. So Andre shines the FTIR beam through the plasma and then examines the absorption at the other end. And from the absorption, knowing that he had ice and his background gas with a small amount of nitrogen and oxygen in there, he can actually back out the phase of the ice grains because they have a very well-known absorption spectrum. There are 17 phases of ice water, by the way, which is pretty wild. So this is a picture of the ice. They're elongated and fractal-like. We've got a bunch of theories on nucleation, but we generally assume actually homogeneous nucleation. This sort of freaks a lot of people out when we say this, but it's similar to a cloud chamber, if you're familiar with a cloud chamber. And these ice grains will exhibit interesting wave-like behavior. So there's sort of new regimes that are unlocked by having a supermassive negative charge carrier in your plasma. This is a selection of videos that Andre has collated. L here describes the length of the long axis of the ice. And you can see that they sort of bob and rotate, and the whole lattice-like structure exhibits large-scale waves as well. So Andre is looking into a lot of different things, including how the long axis of the ice grains may polarize light, how wave-like phenomena propagate, and whether or not they leave any kind of noticeable mark on the overall properties of the plasma. So that's basically it for the set of astrophysical experiments that we have here at Caltech that represent astrophysical plasmas. Is there any questions about those? No?
Are there any other plasma interaction?
No, there are not any dedicated laser plasma interaction facilities at Caltech. We do a lot of laser aided analysis, but we're not doing like laser generated plasma, laser coupled plasma. I know there are some small scale labs that work on that, where they basically generate a plasma with a high energy density laser. But for dedicated large scale facilities, your best bet would be UCLA nearby. They have, I think, some plasma facilities. LAPD.
Yep.
And also,
LAPD is not the
yeah, it's pretty wild. I think Sandia also has some, and they do a lot of academic collaborations. And there's one other one which I'm forgetting. Might be WVU. Anyway, if there are no other questions, I'll blast through the remaining slides and then I'm going to snack. So what are some other relevant experiments? These are a small subset of astrophysically relevant experiments. This is a small collection of associated colleges just from my knowledge, university from my knowledge. There are more jet experiments. The MAGPIE experiment at the Imperial College forms a jet with a particularly interesting mechanism. They have a complex wire array of 16 wires in a conical formation, which they blow apart and then pass a gas shockwave through. And that produces a pretty high energy density jet, which you can see here. They use this for simulating astrophysical systems, but also for doing magnetized beam target fusion. Magnetized target fusion, sorry, not magnetized beam target fusion. There's also an Embry-Riddle Eagle experiment, which is very similar to ours. The difference here is that they have a continuous circular inlet. They don't have those discrete flip points that we have. So this might actually be better at representing physical systems because it has that same initial topology. Another big one is the PHASMA experiment. This makes angled plasma jets to generate merging flux growths. So you have these collimated jets of plasma that are a light angle of inclination, and they reconnect. And this simulates a fundamental astrophysical plasma process, magnetic reconnection between flux groups, to examine how the energetics of forming these large scale structures like solar thermal loops and jets work out in the long term. This is actually similar to our Croft experiment with a totally different topology. It's, in some sense, parallel flux strips merging together and examining the energetics of that. So where we have loops with different foot points, they have lines with different endpoints. Another big one is the magnetized dusty plasma experiment at Auburn University. They have what they call a second generation dusty plasma experiment. It was just completed, I think, in 2014. So it's still a very young experiment. They have these very large cryostats and very large bias coils that they can use to get some pretty interesting magnetic topologies and extremely precise temperature control. They also have a central bore through the cryostat, which permits diagnostic access from above. So you can see this plasma from basically every angle. So they have superior diagnostic access to basically every other dusty plasma experiment on the market. And that's just a small section. Here are my works cited. Yeah, are there any questions? Thank you. I hope you learned a little bit about simulating these interesting systems in the lab and got a line in on some interesting experiments going on. Thank you so much for attending, everybody. I really appreciate it.
I have a question.
Oh.
So the obligatory question of, is this really easier to do than simulating audio?
No, it is not. It is definitely more expensive, more time consuming. I think the more critical thing is that you don't have to deal with some fundamental limitation that can make your result questionable, right? In these experiments, there's no numerical diffusion, there's no questioning your boundary conditions, there's simply measuring mechanical systems and putting sensors where you need sensors. So you trade off flexibility for definitive, I think is the appropriate response. So it's
actually definitive with your setup, your boundary conditions.
I mean, as definitive as you would expect something to be, right? Like we know where our surfaces are and we know what they're made of.
No, I mean your initial step, how close to astrophysical they are.
Oh,
For example, the way you trigger your jet. If some of the jets are triggered by spin of the lab, that's something that you cannot be exactly replicate in your lab. You will have to come up with some other way to trigger those jets. So
yeah, no,
given different initial conditions, given different boundary conditions, how different are your measurements?
Yeah, no, that's an excellent point. I should clarify. I didn't mean that our boundary conditions are definitively the same as the astrophysical systems. I mean, our boundary conditions are definitive in that we know what they are. We can precisely tell what they are. And they don't move around because they're physical. But you make an excellent point, which is that you don't have the ability to precisely make a system that has the same boundary conditions as the astrophysical system without perfectly recreating the astrophysical system. So you sort of have to rely on some of the edge conditions of existence and uniqueness. You have to choose your boundary conditions such that they produce some intermediary state that matches the initial boundary conditions. So typically what I've done in this presentation is I haven't shown you the beginning of the jet. I've shown you the point where it has the same magnetic field topology as the astrophysical system, and then said from here they evolve the same. And that's sort of the trick we often play. If you look at the appendix here, this is what the jet initially looked like. We have 8 arches that merge and then form that jet, which we can say is much more analogous to an astrophysical system. In reality, what you would expect is that there's a current sheet that develops, not individual current like flux ropes. And that's why and that's why, that sent me to the wrong spot. That's why the Eagle system might actually be a better representation, because it has that continuous sheet-like beginning, which more accurately represents what we expect to happen in an astrophysical jet. So I hope that is sort of an answer to your question. Are there any other?
Back on the-
I can't.
Are there any other questions from people attending online?
Yes, please ask questions.
Okay.
What's up, YouTube?
Um, Scale.
No, these systems are not small enough to be dominated by viscous effects. Yeah, yeah, yeah.
What about like
Mhm.
and more relativity?
So that's a great question. Let's see, is this the right slide? No, where's the right slide? Oh, geez, I guess I don't have a great slide for that. Necessarily, the small plasmas are generally going to be more resistive than the actual scale plasmas, and that's for two reasons. One, we can't drive them with the same kind. We just don't have access to the same kind of power. It's really difficult to manage, and we also are necessarily coupled to imperfect power delivery mechanisms. Your power system is going to be inductive. It's going to be capacitive, et cetera, et cetera. So going in, it's very difficult to compensate for the impedance that you're adding to the system that doesn't exist in the astrophysical system. You can back it out. You can actually correct for it. The dusty plasma experiment that we have required an impedance matcher specifically for that reason. Otherwise, you'd end up coupling in all of these strange effects that were basically you just couldn't live with. In the jet, it doesn't quite matter so much because the way it worked out, just we ended up with a system that was low enough impedance that our overall resistance is much less than an ohm. And in the astrophysical case, I think, it's the difference of much less versus much, much less. So factors of 10 versus factors of 100. So I think the answer to the question is you can't always do anything about those non-idealities. There are cases where you can counteract them. You cannot predict them generally. So what we have done is we've just looked at our system, looked at these scalings and said, this is good enough, and rolled with it from there. We partially accepted this because our simulating astrophysical systems is not our only credo. We're also interested in examining fundamental plasma processes and looking into fusion-related plasmas as well. So this is sort of a good balance point.
Why do you not simulate or anisotropic? Why are your temperatures always the same, parallel and perpendicular? Can you even simulate anisotropic?
The answer is we can simulate anisotropic plasmas. I'll be honest, I'm still fuzzy on exactly why they're difficult to generate in the lab. Because I think the best answer I can give is, whenever we strike a plasma in a system like this, we're relying on Paschen breakdown. So we have a new Paschen breakdown. Yeah, Paschen.
Oh,
Yeah. Let me see. This is probably the best. So what happens is you have this neutral gas cone that's injected into your vacuum chamber, right? And at first, your electrodes are not closed; they're not charged. The switch in that main bank is open. So these electrodes are just they're just grounded. You close that switch, one of them jumps to -5 kilovolts. And this basically rips electrons off of the neutral gas, and you get that red arch there. And you do get it in that general structure. That's what we see. And that's Paschen breakdown. It's just the electrons getting ripped off of a neutral gas species to form a plasma because they're exposed to such a great potential difference along some minimal path. It's actually an empirical law. It's not really understood what's driving that, but that's sort of the fundamental mechanism by which we get these plasmas. So they come from already Maxwellian neutral gas cones, because we give these things a lot of time to hang out, and then they're energized by the electric energy from the field that we get from closing the bank and energizing our electrodes. This is sort of like throwing a brick to Mach 2 from steady state. So that is just a highly collisional process. Is the fundamental. You start from this dense neutral gas. Once you start throwing electrons off the
I
particle,
mean, it can be collisional, but and still the plasma can have
anisotropy.
anisotropy in their temperatures parallel and perpendicular.
Yes, no, I know. I'm just saying this particular process typically is not anisotropic because you have that field.
So all right. So you don't inject anisotropic plasma.
Yeah.
You inject isotropic plasma.
Yeah.
But then you let it evolve.
Yeah.
In the field configuration. They can develop an isotropic.
They can. Yeah.
Do they? Or
Typically no.
no, exactly. So why not?
I mean,
is it an experimental artifact that they don't develop, or if you're actually simulating?
Yeah.
If you're scaling everything from astrophysical scale,
it should develop the anisotropy. I think it comes back to what you were saying earlier, that a lot of these plasmas are not, the Lundquist number does not meet the reconnection criteria, because a lot of the heating that causes anisotropy in MHD-like plasma comes from reconnection event, where you have inflows and outflows that energize one species more than another, and then you end up with this parallel perpendicular energization. So I think the best answer to your question, because our plasmas are not typically energetic enough to exhibit reconnection, they stay isotropic rather than developing them in isotropies. We don't have magnetic topologies that have really sharp X points or anything like that. So I think that's the best answer to your question. We do sometimes see reconnection, and we've simulated those things. And we, in our simulation, given our knowledge of the system as it's physically constructed, there is anisotropy when we do happen to have a plasma that is energetic enough to reconnect. Like I said, though, that's infrequent. That's sort of part of the physics that we're working on explaining. And we don't yet have the tools to examine it. That's actually something I'm looking into. When you have these anisotropies, you also expect beaming, right? You're going to have particles traveling faster in one direction than another. So if you have a hot tail, or if you have just that small amount of energized species that are sort of at the edges of your distribution, when they travel, they can actually collide with the chamber wall and produce X-ray. And if there is an anisotropy, then you expect that part of that X-ray distribution is going to be brighter along sort of parallel plane versus the perpendicular plane. If you take a cut to the top. I don't know if I'm making sense there, but
you don't see such an X-ray after glowing.
No, not yet. Part of it is because we don't have the tool to examine that. We're currently developing this tool. But that is an excellent point. Is that our parameter space that we can reasonably represent may be further sheared down by the fact that we don't have plasmas energetic enough to have these anisotropes, or that they don't routinely exhibit these anisotropes. So, we can show what a jet looks like, but we can't tell you what the solar wind is doing.
Is there anything you want from astrophysics?
God, what do I want from astrophysics? Simpler textbooks would be nice. No, I mean, I think I don't have anything concrete. No. A good definition of a flux warp would be nice, though. Are there any other questions? Is that it?
Can we do a real
Oh yeah, absolutely.
what should we do?
Just send me an email. I'm basically in the lab every day, and I can give you a tour literally whenever you want.
Yeah, great.
All right, thanks, everybody.
Thank
Thank
you.
you.